It's time to turn our attention to a different coordinate system than the rectangular system. Newton's second law still holds in this other coordinate system, the normal tangential coordinate system. Of course, we've done these before in kinematics, but now we're going to look at them with forces. So Newton's second law, the sum of the forces is equal to mass times acceleration. That doesn't change. But what we're going to do now is we're going to break the acceleration down into a tangential component and a normal component. We'll also add into this a y component, and you'll see in the next two examples why we put that into play. So we could write this then as mass times the acceleration in the tangential direction times the tangential unit vector plus the acceleration in the normal direction times the normal unit vector. And in our two cases, we're going to add a y component as well. Now keep in mind that the tangential acceleration is the time derivative of speed, not velocity, speed. How is it increasing in speed? Is it decreasing in speed? If it's increasing, we have a positive v dot. If it's decreasing, we have a negative v dot. And then the acceleration in the normal direction is the speed squared divided by the radius of curvature. In our two examples, that will be constant, but it doesn't have to be. And then the y direction would be an up and down or vertical component, and that will become important, and we'll see that here in just a minute. Okay, so let's take a look at our first problem, and we always like to start off by writing down the known values. So as we read through this problem, what do we find out? We find out the radius of the track is 200 meters, and that's going to be a constant. So rho is equal to 200 meters, and the rated speed is 180 kilometers per hour. So what is the rated speed? Now, that's a concept that's new, but what that's telling us is that when the car is on the track, moving at the rated speed, it doesn't matter whether the track is wet or dry, it doesn't matter. Bank, this angle theta here, is made so that the car will go around the track and the frictional force will be zero. Keep in mind, the static frictional force is less than or equal to mu static times the normal force. So in the case of the rated speed, the static frictional force is zero, which is of course less than mu s times the normal force. There's still a normal force, there's still a gravitational force, but the frictional force is zero. So v in this part, I'm going to label this with an A because this is part A of the problem, is equal to 180 kilometers per hour. And if we do a conversion, we find out that that's equal to 50 meters per second. Then it goes on to say, knowing that the racetrack, the car starts skidding. So really starts is the critical word here. What's happening in this scenario is I'm just breaking the static frictional force to where it's kinetic. In other words, less than or equal to for part B becomes not less than or equal to, but equal to. In other words, I'm at that maximum value for the static frictional force. And so in part B, the velocity is 320 kilometers per hour, and that corresponds to 88.9 meters per second. And finally, in part C, the minimum speed, what happens at the minimum speed is opposite of what happens at the maximum speed. So imagine, if you will, you're traveling at the maximum speed. If you're going to start skidding, you're going to go up the track. If you're skidding up the track, that means the frictional force must be down the track. In the case of part C, the minimum speed, and that's what we're looking for, so we don't know that yet, then you're sliding down the track, in which case the frictional force must be up the track. So we're simply going to reverse the direction of that frictional force. We're looking for the angle theta, then the coefficient of friction. In part B, the angle theta will be whatever it was in part A. That won't change. In part C, the coefficient of friction will be whatever it was in part B. That won't change. So there's my known information. So what are the forces acting on the car? Well, of course, I've got mg, so that's gravity due to the earth acting on the car. There is a normal force. Of course, the normal force is perpendicular to the surface due to the track acting on the car. And then finally, a frictional force, which in the part B is going to be down the track. So that's in that direction. So F static. That's friction, also due to the track, and the track is the only thing touching the car, acting on the car. And so I've got the track perpendicular to the track and the track parallel to the track. Those are the two forces due to the track. So the only long-range force, of course, is gravity. I'm done with anything in contact with the car, so that's it for my forces. I always like to know what direction the acceleration is in. So in my case, the acceleration is towards the center of curvature, and that's actually going to be in this direction. So that's the acceleration towards the center of the curve. And of course I need a coordinate axis. Now in this case, we're going to have an axis towards the center of curvature. That will be the normal. The tangential is in the direction of the velocity, and in this drawing the velocity is coming towards us, so that's out of the page. But there's no acceleration in that direction, there's no forces in that direction, so we're not going to worry about the tangential component of Newton's law. Then there's also up, which is of course the y-axis. So I've got a normal direction and a y direction. Now, what about this angle theta? So keep in mind that angle theta on my coordinate axis is here, and so perpendicular to the track is that direction. If this is theta in here, this must be 90 minus theta. This must also be theta here, which means this is 90 minus theta. And if I come down in this direction, this is also theta there. This is vertical angles. So in my drawing, the only theta we have is right there. So there's my angle theta. I better put in a y-axis though as well. Now we're ready to write out the force equations. So we'll start off with the y direction. We can see that the normal force and the static frictional force both have y components. In the case of the normal force, it's up in this direction. In the case of the static frictional force, it's down. This up in the y direction for the normal force is adjacent to theta, so that's going to be the cosine. And opposite of theta is the y component of the static frictional force. So that's going to be the sine of theta. And so what I'm going to get is the sum of the forces in the y. I'm going to have F normal times the cosine of theta minus F static times the sine of theta. And of course, mg is also in the negative y direction. So minus mg. Going back to the diagram, the acceleration is strictly in the normal direction. There's no acceleration in the vertical or y direction, and so this must equal 0. And then the sum of the forces in the x direction, I'm going to have Fn sine theta. Right? The x component of the normal is opposite of theta, so that's the sine of theta. And then the static frictional force is adjacent to theta, so that's going to be the cosine of theta, and both of them are to the right, plus F static cosine theta, and that's equal to mass times the normal component of the acceleration, which is mv squared over rho, the centripetal force. Notice the centripetal force is not a definable force. The centripetal force is always caused by another force. In this case, friction in the normal force. If I had a ball on the end of a string, it would be caused by the string. If I have the Earth going around the sun in a circular pattern, the centripetal force is caused by gravity. So the centripetal force is the net force, or the sum of other forces. It's always the right-hand side of the equal sign. And it must be caused by the forces in the force diagram, in this case the normal force and the static frictional force. So there's my equations. Let's kind of start putting things together. Remember that, recall in part A, F static is equal to 0, because I'm at the rated curve speed. So F static equals 0 in part A. So what that means then is that F normal cosine theta equals mg. I've rewritten the y equation. All I've done is rewrite the y equation. And so I'm going to bring the m into, I'm going to solve this for m and bring it into there. And so I'm going to get in the x equation Fn sine theta equals Fn cosine theta over g times v squared over rho. And so what you're seeing here is the normal force canceling out. And if I divide both sides by the cosine, I'm going to get the tangent of theta equals v squared over rho g, and that's equal to 50 meters per second squared over 9.8 meters per second squared times rho, which is 200 meters. Notice my denominator has the same units as the numerator, 9.8 times 200, and then it's going to be meters squared per second squared, and my numerator is 2,500 meters squared per second squared. Divide that by 9.8 times 200, 1960 meters squared per second squared. My units cancel, which is good, right? Because the tangent of theta should not have any units. So my units have canceled out there. And so I'm left with the tangent of theta then equal to 1.2755. And theta then is the arctangent of that, which is 51.90 degrees. So that's the angle theta at which the curve has been banked. It's pretty steep. Pretty steep bank. All right, let's go on to part B then. We got part A, and theta's going to have the same value. Now these equations actually don't change, but now Fs is not 0. Fs is not 0. All right, so when I rewrite these equations on the next page, and I'm going to leave my theta as everything kind of the way it's at, I'm going to substitute in mu s times f normal, because that's what we're solving for in this problem is mu s. And so I'm going to get Fn, right, so Fn cosine theta minus mu s sine theta. And I'm going to just set that equal to mg. That's my y equation, right? This is the sum of the forces in the y. It's actually not the sum of the forces in the y, but that's where I get it from, because I brought the mg to the other side. And then I have Fn sine theta plus mu s Fn cosine theta equals mv squared over rho. All right, so let's take this first equation. I'm going to solve that for m. And so I'm going to get m equals Fn. That comes out. I get cosine theta minus mu sub s sine theta all over g. And I'm going to substitute that into the second equation. So this is the top equation solved for the mass. And then I substitute that into the second equation. And I'm going to get on the left-hand side Fn, and that comes out sine theta plus mu sub s cosine theta equals m, which is Fn cosine theta minus mu sub s sine theta all over g times v squared over rho. Now the interesting thing here is that in this problem, just like the last one, the Fn goes away, which is actually related to the mass. We'll note then that in any of these three parts, the mass of the car never comes into play. Of course, I was never given the mass of the car, and this is why. It doesn't matter. It doesn't matter. The mass of the car is irrelevant. So I'm looking for mu s. I've got a little work to do here. So I've got the sine of theta plus mu sub s times the cosine of theta. V squared over rho g cosine of theta minus v squared over rho g mu sub s sine theta. And I'm solving for mu sub s. I'm going to bring this term over to the left side and this term over to the right side. And so I'm going to get mu s cosine theta plus v squared over rho g mu s sine theta. And on the right hand side I'm going to get v squared over rho g cosine theta and minus sine theta when I bring it over. Right, this is already negative, so when I bring it over to the left it becomes positive. This is positive, so when I bring it over to the right it becomes negative. And you can see a mu s is coming out of the left side. So I get cosine theta plus v squared over rho g sine theta equals the right hand side. And so mu s in the end is equal to v squared over rho g cosine theta minus sine theta all over, I'll just put the v squared over rho g first, sine theta plus cosine theta. Notice v squared over rho g, v is length over time, and I'm going to square that, and rho is length, and g is length over time squared. So I have length squared over time squared in the numerator, length squared over time squared in the denominator. The units all cancel out. Fantastic. And so what do I end up getting? V squared was 88.8. Not going to worry about units. I've already determined those go away. Rho is 200. G is 9.8. The angle that I'm talking about is 51.9 degrees. So that's the cosine of 51.9 minus the sine of 51.9. And I divide all that by 88.8. And I need to square that over 200 times 9.8 sine 51.9 plus cosine 51.9, and I get 0.448. A dimensionless quantity, but that's alright. Mu s should be a dimensionless quantity. I'm not going to do part C. The only thing we would do in part C that would be different, now I know what mu sub s is. In my frictional equations in here, this becomes positive, this becomes negative, because the frictional force has changed direction. The only thing I don't know in this problem is v, so I would solve that for v.